And with that, we have our next speaker up, Michael Howes. He is a PhD candidate in the Stanford Statistics Department. Yeah, he's going to be talking about optimal matching with CVXPY, and specifically how they do TA assignment in the Statistics Department.
You are. Cool. Thank you. Yeah, so as I've said, this is just a short talk about a nice application of convex optimization in CVXPY and how we use this software over in the stats department to do our TA assignments. And so, yeah, graduate students in statistics like myself have to TA in order to receive funding, and CVXPY is used to assign students in a way optimally, so it's like optimized for their preferences, subject to some constraints on the number of TAs required for each class and how many times each person has to TA. And I've been helping, maintain and run the small bit of software that does this for the last few years, but some version of this code has been used for 15 plus years. And so when I started doing this, the original code was in CVXM, and then I moved it over to CVXPY. And then I've made a few other changes, which is kind of what I'll tell you about today. But yeah, but it's been really fun to be a part of it. And it's also just kind of a nice application of optimization. And so to start, we're going to phrase this like TA assignment problem as an optimization problem. And so the variables are, it's like one big binary matrix indexed by students and courses. And so Xij being 1 means student I is going to TA course J, and from this you can read off which classes each student is going to TA. And then the objective is to minimize the sum over I and J of Xij times Sij, where these Sijs are scores given by the students to classes. So I send out a survey, and then people kind of give a rough ranking of the classes with kind of lower scores, meaning they more want to TA a class. And so here we're trying to give people classes they want to TA by minimizing this sum. And then there are constraints. So for instance, if you fix J and sum over I, you get the number of people who are TAing course J, and that has to equal some allocated amount that's based on historical course enrollment. And then likewise, if you fix I and sum over J, you get the number of times each person's TAing. Also has a bound if people can't TA too much. And then there are more complicated things, like this assignment is done once at the start of the quarter, at the start of the year for all quarters. So we make sure people don't TA twice in the same quarter. There are rules about how many first years can TA different classes. But fortunately, all of these constraints end up being linear in these Xi variables. And so what we get is a nice Boolean LP. But and here's a nice example to keep in mind where there are just 3 courses and 4 students, and each student has to TA 1, their budget, and then the courses require 1 or 2 TAs. You can see student A like course 1, and be kind of okay with TA course 2 or 3. Student B also likes course 1, student C likes course 3, and student D likes course 2. The real problem that we solve is bigger, but it's not huge. It's 50 students, 70 classes, and it has these more complicated constraints. But one thing that's true of this example, and also the big one, is that typically the optimal assignment is not unique. Here you can see student A and B gave the exact same scores for course 1 and 2. So any allocation in they're teaming those 2 classes, you can just swap them, and that would be equally good. And this is very common in the actual solution. There's 2 or more students give same preference for 2 or more classes. So then you get multiple solutions. So I mentioned that the code base is pretty old. It hasn't maybe changed so much. I think me moving from CVXM to CVXPY was the biggest change in a while. And so we definitely haven't kept up to date with the changes that have been going on in the CVX world. And so what the code did when I received it was it relaxed this Boolean LP to a linear program. I don't know if there were Boolean LPs in CVXM 15 years ago, but there were certainly linear problems. And so then by relaxing, we get we allow for fractional assignments. And then this becomes a nice linear program, which is very easy to put into CVXM or CVXPY. And then you get so that, looks just like this. And then you get an allocation, but typically that's not going to be Boolean. And so here you see the optimal allocation gives half and half, which is, I guess, fair. Both of these students would rather TA course 1, but we don't allow fractional assignment. And so the code I inherited had like a big complicated rounding step where we like pick students and then look at these fractional scores and then based on that assign them, and then they will and then like iterate through different students and like try to make sure the constraints are holding at every single step. But this was lossy, and so it has to be done many times. And then if you want to add a new constraint, like the administrator's like, oh, we want people to TA different classes each quarter, you'd have to put it both in the like CVX part of the code and in the rounding step. And so it was like a bit of a mess. And so the first thing I did was, if you just specify the solver, you'll use simplex method, and then you're much more likely to get a binary solution. And I was very happy about this. But then I realized, like, actually, although I think like Julian in his talk mentioned this, like CVXPY, you wouldn't necessarily think that it does integer programs or Boolean programs, but it does. And Harp says this feature is ancient, but not something I had learned about in EE364A. But if you just say, I want my X variable to be a Boolean, it will solve it exactly. And it easily scales. So like the kind of medium-sized problems that we have. And so now the code is like, more than twice as simple, I think, because we don't have any rounding. And also we get like better allocations at the end. And so I think it's underrated or underappreciated that CVXPY does non-convex things. And I was like very happy to learn that recently. That's kind of what the code base does. There are like a few additional things like having to format data and send out the survey and stuff. But now that this is the CVXPY part. But I want to end with like a small question, which like not necessarily to be answered now, but I'll be around for the day and very happy to talk about these things over lunch. The story I've told is like very nice. We get these optimal assignments right at the start of the year. But then things change, like classes have higher enrollment, students graduate early, and this essentially changes the constraints of the problem. And then currently there's like a very manual thing in which we do like swaps to find the new assignment that like is hopefully still close to optimal and doesn't involve changing too many things. But I think that like this swapping procedure can be formulated as an optimization problem. Now you want to optimize both for the student preferences and for the new assignments being like sort of close to the existing ones, and then you trade off on these two objectives. And so I have some ideas about how this should be done, but if people have thoughts, I'll be very happy to hear them. So thank you.